In this video, we'll continue looking at categorical variables, but now we will look at hypothesis tests. We'll talk about the 4 steps in hypothesis testing. We'll talk about the definitions and notation that we'll use when we're working with hypotheses. We'll look at the 3 different forms of the alternative hypothesis. We'll consider the p-value for a hypothesis test. And we'll start with an example using the greater than alternative. We'll look at some of the other alternatives in the second half of this video. In the 4 stages of statistics, we are in statistical inference, and we're looking at one categorical variable and hypothesis tests. So remember, there were 3 ways that we could talk about inference when we had 55% of a sample eating breakfast. First, we could talk about a point estimate, that is, just what number would be our best guess for the proportion in the population. Next, we could talk about the interval that ought to contain the proportion. So that doing the confidence interval helps allows us to work in measures of the spread in our sample to tell us not just what the estimate would be, the point estimate, but also how far off we think we might be. The third type of problem, which we'll be talking about in this video, is the hypothesis test. One example would be, do more than half of all students eat breakfast? We'll work toward answering that question now. There are 4 steps in completing a hypothesis test. Before we begin, though, we must first pose our question as a choice between 2 opposing views about the unknown population parameter. Once we have the question posed as a choice, we will perform our 4 steps. First, we'll check and make sure that our data production was good and that it did not create bias. Next, we'll summarize using p-hat and we'll standardize to z. Remember, p-hat is the proportion in our sample. Next, we'll find the probability of seeing a p-hat that's this extreme. That is, what is the probability of getting a sample as weird as ours or weirder? And finally, we'll perform the inference. We'll draw conclusions about p based on p-hat. Now, it's worth noting, and you may have noticed, that these 4 steps correspond to the 4 processes of statistics: data production, summarizing, probability, and inference. So let's talk about that first sort of hidden step, posing the question as a choice. So recall our situation. 446 students is the size of our sample. 55% ate breakfast. Do more than half of all students at that university eat breakfast? Now, we need to pose this question as 2 opposing points of view about p. The question involved the phrase more than half. So we can ask, is p equal to 0.5 or is p greater than 0.5? Those are 2 opposing points of view. Now we'll check the data production. We saw this in our last video, but since we're taking a sample using a survey of 446 college students, all taking stats, remember, we want to make sure the sample is representative. That's why we're restricting our discussion to that university. Are the responses unbiased? So we're asking, is this question sensitive? And we didn't think that it was. These address the center of our distribution. For the spread, we want to talk about whether the sample selection process was independent. That means the population needs to be greater than or equal to 10 times the sample size. And since this is a large university, it is. And to talk about the shape, is n large enough? That is, we want to make sure that at least 10 fall into our category of the category in question, and at least 10 are not in the category in question. Now we summarize and standardize. Remember, when we're talking about sample proportion, p hat is a random variable. Its distribution depends on the sample size, but its center, the center of the distribution, is p, and the spread measured by the standard deviation is p times 1 minus p over n, all under a square root. Now, when we do a hypothesis test, what we're going to do is assume that the population proportion is the value that we proposed when we asked the question as two opposing views of p. Remember, our question was, is p equal to 0.5 or is p greater than 0.5? So what we're doing is we're going to take this assumption about p being equal to something, and we'll use that for p in our computation of the standard deviation. Notice that's different from what we did for confidence intervals. For confidence intervals, we used p hat to plug in for p into this formula. When we're doing hypothesis testing, though, we want to take the value for p that was asked about in our question and use that to compute the standard deviation. So in our example, how are we going to summarize the data? We'll summarize the data that we see with p hat. To standardize, we will take our observed value and subtract our mean. And remember, here we're using our half to represent p, and we divide by the standard deviation. So we get a z-value of 2.11. That's a pretty unusual number. Remember, anything more than 2 standard deviations from the mean is unusual. So next we'll find a probability. What's the probability that if the population looks like what we assumed it looks like, what's the probability that we get a sample as weird or weirder than ours? So remember, we got a standardized score, a z equals 2.11. Since in this case we want to know if p is greater than 0.5, weirder than 0.55 would be greater than or equal to 0.55. Well, looking at the 68, 95, 99.7 rule, 2.11 sure enough is bigger than 2. So the probability that z is greater than or equal to 2.11 is less than 0.025. We can use our calculators to find that number exactly. That probability we will consider to be fairly unlikely. Here's the picture. The probability of that tail right here, we're going to call that the p-value for this hypothesis test. Now let's perform the inference. Remember, we got a z-score of 2.11, and we got a p-value, the probability of getting a sample that weird or weirder, as about 2.5%. What's the conclusion we draw about p? Well, remember, either p is equal to 0.5 or it's greater than 0.5. That was the question as we framed it. If p is equal to 0.5, the probability of getting a z as weird or weirder than ours is less than 3%. That's really unlikely. So we'll conclude that p is greater than 0.5. Now let's start talking about some terminology. Remember that we're going to start by framing our question in terms of two opposing values about p. We have names for those, the null hypothesis and the alternative hypothesis. We'll consider the sampling and study design. We summarize with p hat. We'll standardize it to z. We'll assume that p is equal to p naught. and that P naught is the P that comes out of H naught. That is the null hypothesis. And then we'll measure the largeness of Z. We'll find the probability that P hat is this high or low or different, depending on how we phrase the question. That's the P value from the test. We'll see if that P value is small. Then we'll do the inference. We'll draw our conclusions about P. In the context of a hypothesis test, the inference means we're going to make a choice. We're going to make a choice between the null hypothesis and the alternative hypothesis. So, notationally, the null hypothesis is H sub 0. We'll usually read that as H naught. The alternative hypothesis is HA. P naught, or P sub 0, we'll usually say P naught, is the proposed value. It's the value of P that comes from the null hypothesis. The P value is the probability of getting a sample as weird or weirder than ours. So, the null hypothesis, which we will denote H naught, is the claim that the parameter, that's the actual value in the population, is equal to some proposed value. It's worth noting that H naught will always be in the form H naught is P equals something. The alternative hypothesis will be the claim that the parameter is different from our proposed value. It will be phrased in terms of an inequality. The P value is the probability that, under the assumption that the null hypothesis is true, that we get a sample as weird or weirder than the one that we see. Earlier, we did consider the probability of getting as few as 0 red cards and 4 or 5 picks, assuming that half the cards in the deck were red. It's related to the question that we're looking at now. So, notationally, remember, P naught is the proposed value of the population proportion that comes from the null hypothesis. So the null hypothesis will always take the form P equals P naught. The alternative hypothesis will always take the form of an inequality, depending on the way the question was asked. Whether the inequality is greater than, less than, or is not equal to will affect how we proceed after the first step. So look at these 3 problems. We're looking at the problem that we've seen before of picking the number 7 at random from the numbers from 1 to 20. We looked at commuters. 111 out of 230 in the survey were walkers. Do fewer than half of the commuters walk? And the percentage of disadvantaged students in Florida community colleges is 43%. Is this particular college, Florida Keys College, unusual, with 47.5% disadvantaged? In each of these cases, are we trying to draw conclusions about a sample proportion or a population proportion? They're all about population proportions. It's important that you remember to keep the sample proportion and the proposed population proportion separate. Now, in these same 3 problems, what are the alternative hypotheses and the null hypothesis? In the first one, the null hypothesis is 0.05. That's the probability that one of the 20 numbers from 1 to 20 is chosen at random. But we think people might be biased in favor of choosing the number 7. So our alternative would be phrased as P is greater than 0.05. That is, we expect that number to be greater. In the second one, the question is, do fewer than half of all commuters walk? So our null hypothesis is 0.5, and we get that from half. And because it says fewer, we'll frame the alternative hypothesis in terms of less than. In the third case, the null hypothesis is that Florida Keys College is the same as every other college, 43%. The question is 47.5 the actual value unusual? Because we're not making a claim that it is higher than expected or lower than expected, we'll use is not equal to. So here are some definitions. A one-sided alternative uses a strictly greater than or strictly less than sign. The two-sided alternative hypothesis uses as an is not equal to sign, like that. It's worth noting that when we're looking at a one-sided alternative, sometimes you'll see in words it phrased in terms of greater than or equal to, or less than or equal to. Our computations are going to work out the same either way, so we're always going to stick with strict inequalities. It's worth noting that if the sample proportion is on the wrong side of the null proportion, then there's no need in going any further. For example, the moon has 4 phases: new, first quarter, full, and last quarter, and each is in effect for 25% of the time. A neurologist claimed that patients' seizures are triggered by a full moon. They found that 20% of the seizures occurred at the full moon. Do we need to actually go through the process here? Well, the alternative would be, remember, the neurologist says the patients claim their seizures tended to be triggered by a full moon, which means we ought to see seizures more than 25% of the time. But in fact, we only see seizures 20% of the time. Well, that's less than 25%, so there's no way this is going to be strong evidence for the alternative hypothesis. There's no need to go on. Now, when we're doing a hypothesis test, we're going to have a p-value we need to assess. Remember, the p-value is the probability under the assumption that the null hypothesis is true, that we get a sample as weird or weirder than the one that we actually got. Now, the way that we find the p-value depends on the form of our alternative hypothesis. If the alternative hypothesis is that p is greater than the p0, that's the probability from the null hypothesis. With greater than, we're going to look at a right-tailed probability. For less than, we'll look at a left-tailed probability. And for is not equal to, we'll use the area in both tails of the distribution. So if the alternative hypothesis uses is greater than, we're looking for the area in the right-hand tail. If it's less than, we're looking for the area in the left-hand tail. And if our alternative hypothesis is phrased in terms of is not equal to, we need to find the area in both tails. There are 2 conclusions that we can draw once we find our p-value. If the p-value is small, we'll reject the null hypothesis, and we'll conclude that the alternative hypothesis is true. That doesn't mean the alternative hypothesis is true. It just means that we have strong evidence in favor of the alternative. Again, that's not the same as proving that the alternative hypothesis is true. It's just a claim about the strength of our evidence. If the p-value is not small, then we don't reject the null hypothesis. Our conclusion is that the null hypothesis might be true. Again, we haven't proven that it is true, just that we don't have enough evidence to say that it's not. So let's look at an example. Remember that in our sample of 400 students, 30 chose the number 7 at random from among the numbers from 1 to 20. Our question is p greater than 0.05? Remember, p is the proportion in the population. Do we have evidence of bias? In other words, is more than 5% of the population likely to pick number 7? Well, first let's formulate our hypothesis. The null hypothesis is that p is equal to 0.05. The alternative hypothesis is that p is greater than 0.05. Students aren't typical, so we need to worry about bias, but I don't think we have anything to worry about here. Next, we'll check. We see a p hat of 0.07, which does seem to support the alternative hypothesis. So we'll continue. We'll standardize p hat to get a z-value of 2.29. Now we'll compute the p-value. We can use our calculators to find the area to the right of 2.29 under the normal distribution. That gives us a p-value just a little bit bigger than 1%. That's small enough to reject the null hypothesis. The conclusion is that we have evidence of bias in general for the number 7. Notice that since the alternative hypothesis was framed in terms of is greater than, the tail whose area that we wanted to find was a right-handed tail. The area in that right-handed tail was just over 1%. Now, we can use the 90, 95, 98, 99 rule, but again, I'm not asking you to remember those numbers. We can get all of this with our calculators. So if you need to find these areas, don't worry about this, this diagram. You'll need to use it for some of the homework problems, and these numbers will be given to you, but in general, we'll use our calculators to find these p-values. Now let's move on to the second half of this lecture, in which we'll talk about the other forms of the alternative hypothesis. That's less than or is not equal to. We'll look at how the form of the alternative hypothesis affects the tests that we do. We'll talk about statistical significance. We'll look at hypothesis tests in the long run. And we'll relate test results back to confidence intervals. Now remember, when we're doing hypothesis tests, the first thing to do is to state the null and alternative hypotheses. The null hypothesis is the claim that nothing interesting is going on. The status quo holds. The alternative is that something unusual is going on. The alternative hypothesis has 3 possible forms. To do the hypothesis test, we must first consider the sampling and the study design. We will summarize our data using p-hat. We'll standardize under the assumption that the null hypothesis is true. And we will look at the size of that z. We'll use the size of z to compute a p-value. That's the probability that our z that we observe is weird. So that's the probability that if we were to do another sample under the assumption that the null hypothesis is true, that we would get a sample as weird or weirder than ours. What we want to do is see if that p-value is small. We'll talk more about how small it has to be later. And then, based on the size of that p-value, we'll choose either the null hypothesis or the alternative hypothesis. So let's look at sampling and study design. Remember that the sample size had an effect when we were doing confidence intervals. When we were checking the sample size, remember we required that the observed counts both in the category of interest and outside, had to be at least 10. That is that n times p hat and n times 1 minus p hat both had to be at least 10. For hypothesis tests, we require the expected counts in and out of the category of interest to be at least 10. Remember, when we're doing hypothesis test, we first make the assumption that p is equal to p naught. That is, we're assuming the null hypothesis is true. So we want n times the null proportion to be greater than or equal to 10, and n times 1 minus the null proportion to be greater than or equal to 10. Notice the difference between these. So looking at the students choosing random numbers from 1 to 20 again, we want to test our hypothesis. The null hypothesis is that p equals 5%. The alternative is that p is greater than 5%. Now, is n large enough in this case to justify using the normal distribution? Since we're doing a hypothesis test, we use p from h naught. That's the 0.05 we see here. We'll use that here. When we plug that in, we get 20. That's sure enough greater than or equal to 10. We also need to subtract from 1 and multiply that by the sample size. That's way bigger than 10. So yes, we are good to go using the normal distribution. When we did confidence intervals, we didn't have an alternative hypothesis to use. Instead, we used the 30, the actual count in our sample. We wanted that to be bigger than 10, and the number in our sample that were outside of our category. That's 370 in this case. So when we have a greater than in the statement of our alternative hypothesis, we need to check 3 things in step 1. That the sample is unbiased. That tells us that the sample proportion is a good estimate for the population proportion. We need to check the size of the population, that it be at least 10 times the sample size. That made sure that the standard deviation computation was correct. And we needed to make sure that both n times p naught and n times 1 minus p naught are at least 10, which allows us to use the normal distribution, which is what we use to find our p-values. For the less than alternative, here we're looking at commuting students and how many of them walk to school. Here you see the output that a computer gave for this proportion. You see our count and our sample size. Sample p, hey, that's p hat. Then we get the 95% upper bound. So that's the upper bound for the 95% confidence interval. It's presumed that you can use that number, 0.5368, and the sample p, 0.4826, to compute the lower bound for the confidence interval. You just go the same distance in the other direction of p hat. And the computer also found our z value and our p value. Notice that the alternative is framed in terms of less than. So we would expect a negative z value because that's below the expected value. So the question is, can we conclude that fewer than half of this university's commuters walk to school? Well, again, our null hypothesis is that it's actually equal to 1/2. That comes right out of the question. The alternative is that p is less than 1/2. We need to make sure that our sample is good, and assuming that it is, we need to check the n times p, and here I'm talking about p from the null hypothesis. So 230 times 0.5 is 115. Sure enough, that's greater than or equal to 10. 1 minus p is also 1/2, so that'll give us the same number. So we're good to go there. We see p hat is 0.48. We get a z-score of negative 0.53. That's not terribly large. In fact, we get a p-value of 0.299. That's about 30%. Is that small? No, not really. Do we have enough evidence to reject the null hypothesis? Because the answer to the last question was no, we will say no. What's our conclusion? The conclusion is that the null hypothesis could be true. Now again, because the z's are continuous, whether we use a less than or equal to does not matter. We get the same number either way. We also saw an example that talked about disadvantaged students in the Florida community college system. 43% of those students were reported to be disadvantaged. At Florida Keys Community College, we see 169 out of a sample of 356 disadvantaged. Is that an unusual number? So here we frame the alternative hypothesis in terms of is not equal to. Remember, the null hypothesis says that there's nothing interesting going on, that what's happening at Florida Keys is typical of the rest of the community colleges in the state. We notice that n times p and n times 1 minus p are both greater than or equal to 10. We also here, we're assuming that the population, the student body size at Florida Keys Community College is greater than or equal to 10 times 356. You can assume that that's true. We see our p hat from our sample is 0.475, which standardizes to a z-value of 1.7. The p-value in this case is 2 times the probability that z is greater than or equal to 1.7. The reason why we're using 2 times here is because we need the area in both tails. Is this small? No, not really. Do we reject the null hypothesis? No. So is 47.5% unusual? Well, it might be, but it's not unusual enough for us to say that the null hypothesis is false, or that we have enough evidence to reject the null hypothesis. So again, because the alternative hypothesis was framed in terms of is not equal to, we've got to find the area in both tails. We get that by finding the area in one tail and multiplying by 2. Now let's talk about doing these hypothesis tests using our calculators. The hypothesis test that we want can be found in the stat menu, and we're going to go over to tests. We're doing a test for a single proportion, so you see that as option 5. And notice that it asks you for 4 things. First, it asks you for p0. Remember, that's the proportion from the null hypothesis. So if we want to do the example that we saw from the community colleges, the proportion, according to the null hypothesis, was 43%. So I'm going to type that in as 0.43. Now in the sample that we saw, 169 out of the 356 sampled were disadvantaged. So x, that's the actual value in our sample, the actual count in our sample, that's 169. And our sample size was 356. Now next, we're asked to frame the alternative hypothesis so that the calculator knows which p-value to report. You'll use the arrow keys to select the one that you want and push enter. In the last time we looked at this example, we were looking at whether the observed proportion was unusual. So lacking anything else, we'll use is not equal to. So I'll hit enter. That selects it, so I'll use the down arrow to get to calculate, and I'll push enter. And first line reports our our alternative hypothesis. We get our z-score, our p-value, our p-hat, that's the proportion in the sample, and the sample size. So here we get a p-value of about 8.8%. That's just like what we saw on the previous slide. Here's a picture. Notice that our z-score of 1.7 falls in a little bit bigger than 1.645. So the p-value that we got is just a little bit less than twice the area in the two tails. Now, remember that the form of the alternative changes the p-value. The two-sided alternative will have a p-value that's twice as big as the one-sided. The p-value is the deciding factor when we're doing the test, so the p-value is of critical importance. Because of the importance of the p-value, it is critical that the alternative is framed before we consider the evidence. Otherwise, this is sometimes called snooping at the data or mining the data. We don't want to take a look at the data first and then find something unusual in the data and say, oh, look, here's this weird thing. We thought this was there all along. If it's not obvious which of the two greater than or less than we should use, then we should always stick with the two-sided alternative. In the community college example, we're just asking if the percentage disadvantaged at Florida Keys Community College is unusual. And again, we want to answer that question before we know what the actual proportion is in our sample. So we don't know that our sample ended up having a strangely high number. Now, if the question were framed instead as, is the percentage unusually high? That means we think ahead of time that that's strange on the high side, and we'll frame our alternate hypothesis in terms of is greater than. If we change it to is greater than, we get a p-value of 0.044. Nothing has changed in the data production. We have the same p-hat. We have the same z. It's worth noting that our p-hat is on the side of the alternative hypothesis that's correct. Now we get a p-value of 0.044. Because our alternate hypothesis was one-sided, is greater than, we're looking for the tail to the right. Is that small? It's definitely smaller than the 0.088 we saw with the two-sided alternative. But for what we're going to establish in a moment, yes, we're going to call that small. So is 47.5 significantly higher than 43%? Yes. Now remember, in this case, we're talking about is it significantly higher? We found that our p-value gave us that yes, the 47.5, the observed percentage, is significantly higher. But if we change it to a two-sided alternative and simply ask, is 47.5 significantly different than 43%, our answer changes to no. That's why it's important to make sure that we pick the right alternative. Always, the one-sided alternative will have a p-value that's half the two-sided alternative p-value. Another way to say that is that the p-value for the two-sided alternative is twice as big as the p-value for the one-sided alternative. Again, that's why it's important that we choose this before we look at the data. Because the two-sided alternative has a bigger p-value, that's considered to be a more conservative choice because it makes it more difficult to reject the null hypothesis. Now, before you go jumping into doing a hypothesis test, always look at the evidence that you've got first. For example, if we're looking at the community college example again, and we ask if the rate at Florida Keys is significantly lower, there's no need to do the hypothesis test. We actually have evidence that it's higher. We can't use this as evidence that the actual proportion is lower. So, how small is small? We'll define the cutoff level for the significant p-values as alpha. Alpha will be the cutoff level for a p-value that is, quote, small. Now for us, unless we state otherwise, we're going to use an alpha of 0.05. That doesn't mean that we have to always stick to that. We don't want to blindly stick to that level. When we're trying to decide what alpha should be, we want to take several things into account. Like how set in stone the null hypothesis is. We also want to ask, what would be the consequences of getting it wrong? If we reject the null hypothesis when in fact the null hypothesis was true, or if we reject, or if we fail to reject the null hypothesis when in fact the null hypothesis was wrong. We want to make sure that we don't make a critical error that could be dangerous. So, remember our examples. There were 3 of them that we've been looking at in particular. The random number selection, the commuters walking, and the disadvantaged students in Florida. So based on the p-values, what were our conclusions? The conclusions that we drew were all consistent with using alpha of 0.05. So if the p-value is 0.01, we will reject the null hypothesis because that's smaller than our alpha of 0.05. If our p-value is 0.299, we will not reject the null hypothesis because that's bigger than 0.05. For a p-value of 0.08, we will not reject the null hypothesis, but for a p-value of 0.044, we will reject the null hypothesis. So here's another example. A bookstore chain is going to open a new store in a city only if there's evidence that its proportion of college graduates in the new city is higher than the national rate of 0.26. What should we use for our cutoff? If no other information is provided, or if the chain is enjoying considerable profits and the owners are willing to take a chance, or if the chain is in financial straits and is more risk averse as a result. So if no other information is provided, we'll use 0.05. If the chain is doing well and is willing to take risks, we'll use the easier cutoff to attain, that 0.1. So it'd be easier for us to get a sample that falls under that alpha level. But if we're being more conservative because we're more risk averse, we want to choose a stricter alpha, like 0.01. So we'll use the term statistically significant to indicate a p-value that's small enough to reject the null hypothesis. Remember that the z-value, that's the observed minus the expected under the assumption that the null hypothesis is true, divided by the standard deviation. That can be rewritten using some algebra in this other form on the right. We reject the null hypothesis if the p-value is small, which corresponds to z being large in absolute value. That's going to happen if p hat is far from p naught. If that difference is big, that's going to make z big. If n is big, that's also going to tend to make z big, because after we simplify that expression, the square root of n appears in the numerator. We're also going to get a big Z if the denominator is small. That is, if the null proportion is close to 0 or 1. Let's look at sample size in particular. For a large n, we might reject the null hypothesis, even though what we see isn't really all that different. So remember, a very small p-value is strong evidence against the null hypothesis. But that doesn't mean that we have a really weird-looking sample. For a small n, we might not reject the null hypothesis because that small sample size doesn't give us enough information. So we may fail to reject the null hypothesis even though the null hypothesis was false. Failing to reject a false null hypothesis is called an error of type 2. A type 1 error is the error that we make by rejecting the null hypothesis even though it's true. That's like a false positive in a test. A type 2 error is failing to reject a null hypothesis even though it's false. So that's a false negative. The probability of making a type 1 error is our cutoff value of alpha. That's a good way to interpret that alpha. Now, how do we interpret hypothesis tests in the long run? If we do 20 coin flips, so we're doing samples of size 20, we do it over and over and over and over again. And we do these hypothesis tests, testing the hypothesis that the coin is fair and that the probability of getting heads is 0.5, using a cutoff of 5%. In the long run, we'll get 5% of these tests rejecting the null hypothesis, even though it's true. That's the nature of these hypothesis tests. It comes about from the nature of the randomness in the process of getting the sample. So here's what it looks like. If we do 20 coin flips and we get 9 heads out of 20, that's the first line there. That's a sample proportion of 0.45. We compute a p-value of 0.655, so we do not reject the null hypothesis. If we get 8 heads, that's also not enough. 12 heads gives us a p-value of 0.37. That's not enough. If we get 15 heads, that gives us a p-value of 0.025, which is enough to reject the null hypothesis. So if we do this over and over and over again, eventually we will see an example of a rejection of the null hypothesis that was actually true. If our p-value, our cutoff, alpha for p-values is 0.05 or 5%, that means that 5% of our hypothesis tests will result in a type 1 error. Let's take a moment to look at the connection between confidence intervals and hypothesis tests. Remember, the confidence interval is a range of plausible values for the unknown proportion in the population, whereas a hypothesis test decides whether a value that we see in a sample is plausible. So here's another way to think of it. If the null proportion is in our confidence interval, in general, we do not reject the null hypothesis. If the null hypothesis is outside the confidence interval, we will reject the null hypothesis. So if we construct our 95% confidence interval for a proportion of students choosing number 7, remember we got 0.055 to 0.095. If we frame this in terms of a hypothesis test, where the null hypothesis claims that p is equal to 0.05 with the alternative that p is greater, what do we think will happen? Well, look at the confidence interval. The null hypothesis proportion, that p0, which is 0.05, does not fall in the interval. So at a 95% confidence interval, the null proportion is not in there. So at alpha equals 0.05, we would expect the hypothesis test to reject that null hypothesis. So let's say that a hypothesis test did not reject the null hypothesis in favor of the alternative framed in terms of a less than. What can we say about the confidence interval? Well, if it did not reject the null hypothesis, which was that p is equal to 0.5, we would expect that, yes, 0.5 would be inside that confidence interval. So this was a long one. Here are the things we talked about. We talked about the 4 steps in performing a hypothesis test, checking the data production, summarizing and standardizing our observed values in the sample, finding a p-value based on that, and then inferring a conclusion about the population. We talked about how to create null and alternative hypotheses. We looked at definitions and notation of all these, as well as the 3 ways that we could frame an alternative hypothesis: greater than, less than, or is not equal to. We talked about how to assess the p-value, whether it's big or small. We first looked at an example using the greater than form of the alternative hypothesis. Then we looked at examples of the other ways to frame the alternative. We looked at how the form of the alternative hypothesis could affect the results of the hypothesis test, because the 2-sided hypothesis will have a p-value that's twice as big. We also looked at when the data do not give support from the beginning, which means we don't need to carry out the test at all. We saw the p-value for 1-sided alternatives is half as big as 2-sided. We decided, unless otherwise stated, that our cutoff for small in terms of p-values would be 0.05. We talked about statistical significance, the role of the sample size, and type 1 and type 2 errors. We talked about what hypothesis tests look like in the long run. And we talked about the relationship between hypothesis tests and confidence intervals.